Hello, lucky students. You are being treated to another video from your awesome teacher, Matthew Shepard. Okay, we're going to start section 9.2.2 today. Make sure you've got paper, pencil right in front of you. Make sure you're answering things both on your paper and on the computer. Our essential question today is, what is so special about a right triangle? And we're going to learn about the Pythagorean theorem today. Many of you guys are familiar with it. We're going to dive in deeper and we're going to connect it to some of the things we've already seen in previous classes. In lesson 9.2.1, that's what you did yesterday, you saw that for three lengths to form a triangle, they must be related to each other in a special way. Today, we're going to investigate a special relationship between the side lengths of right triangles. This relationship will allow you to find the length of a missing side. Okay, so use your patterns from lesson 9.2.1 to decide if the squares listed below will form a right triangle. Okay, so first A, if we had squares with side lengths 6, 8, and 10 meters. Okay, well, first of all, if I've got my squares, one with, we're going to call that length of 6, slightly bigger one, that had length of 8, and then here's going to be this other one, larger than each of them, and that one's going to be 10. So in the middle there, I'd have my triangle. Now we want to know if that would form a right triangle. One of the things we learned is that if we add up the areas, so the area of the one with length 6 would be a 36. Area of length 8 would have, would be of length 64. And the area of the square with a length 10 would be 100. Now what I do notice is that the two smaller areas, 36 plus 64, do in fact equal 100. So the sum of the two smaller squares equals the area of the final. Therefore, A is a right triangle. B, squares with areas. So now they're giving us the area, not the side lengths, of 64, 100, and 144. Okay, well that's easy enough to test. Once again, we know that the two smaller areas should add up to equal the others. So if I try to add these up, 64 plus 100, would it equal 144? No. So it would not be a right triangle. And in fact, that would be greater than. So because the sum would be greater than, we actually know this would become acute. Two squares with side lengths 5 feet and a square with an area of 50 square feet. So we got two squares, each of them have a side length of 5. Now, that's the side length, and a square that has the area of 50. So we're now dealing with two different things. So if I were to draw this, what they're saying is this one had a length of 5, this one had a length of 5, and then this final one had an area of 50. Okay, well, my area of these smaller ones should be 25. 25. So, if I had 25 plus 25, does that equal 50? Yes. And so the sum of the areas of the two smaller would equal the larger. That would form a right triangle. All right, D. Explain how you know whether three squares will join at their corners to form a right triangle. Okay, this is what we've been saying. We learned it yesterday. We're covering it again right now. We've just seen it 3 different times. The sum of the smaller areas, sorry, it is not easy to write on this, will equal the area of the largest square. Okay, that's how we know. Alright, so the Pythagorean relationship. Based on your work so far, if you know the area of 3 squares, you can tell if they will connect at their corners to form a right triangle. We know this by comparing those areas. But what if you know that a triangle already has a right angle? What if we start out knowing that it's a right angle? We're not trying to figure out if it will form a right angle. We know it's already a right angle. Will the lengths of the sides be related in this way? Work with your team to look more closely at side lengths of some triangles. This is really going to require that you've got your paper in front of you. On your paper, use the grid lines on it to draw a triangle that has one length that goes straight down and is 5 squares down. The other should go 12 squares across. After you've done that, use something straight to draw a straight line from one corner to the other to form a triangle. Now, because our first 2 legs went straight up and down and straight across, we know this will form a right angle. Once you've drawn in that triangle, you've successfully answered 969A. Make sure to label it properly. 969B. Measure the longest side of the triangle and label its length. Now, this is going to be a little bit tricky because in order to do so, I apologize. In order to do this, one of the things you're going to have to do is to use some of the squares on another paper to measure. We can't just count all the squares that this diagonal has passed through. You're going to have to take a paper and turn it slightly so that all the squares on that paper perfectly line up with that line. And then you'll count how many squares across that one is. Now, we already know what we counted for the other sides, but we need to count out how far this one is. Okay, so take a moment or so. It may be a little bit tricky, but take a moment, take another piece of Cornell note paper, turn it a little bit so that you can count exactly how many squares across that triangle was. Okay, now if you've done this well, you should have arrived at a number very close to about 13. Okay, if you've done this correctly. Now, visualize a square connected to each side of the right triangle. On your paper, sketch a picture like the one at the right. What is the area of each of those squares? Is the area of the square that is connected to the longest side equal to the sum of the area of the other 2 squares? So we add 5 to 12. So if I'm going to draw this, we add 5, we had 12. So if I'm now drawing on the squares that would have formed this, okay, and now trying to find the area of these, well, the area of this bottom one would have been 144. Over here, 25. Now, once again, we should have gotten something close to 13. So let's start with that number. If this was of length 13, 13 times 13 would give us 169. So 25 plus 144 equals, sure enough, 169. And so the lengths actually did meet up. We started with something that we knew was 90 because we were going straight up and down and straight across. And sure enough, the areas once again add up perfectly to the length of the larger. So check this pattern with a new triangle. Draw a new right angle on the centimeter piece of paper just like you did in Part A. This time use 9 squares across and 12 squares for the length and the width. Connect the endpoints to make a triangle and measure the third side again. Okay, so once again you're going to have to turn the paper, maybe use a different Cornell note paper so that you can accurately count the exact amount of squares. Once again, you can't count the squares on a diagonal. You're going to have to make your diagonal match up perfectly with another paper. Create a sketch for this triangle just like you did. Find the area of those squares. So once again, draw those two triangles. Draw the one triangle and the 3 squares that go on top of it. Find the areas. Okay. Is the area of the square that's connected to the longest side equal to the sum of the other two? If done properly, then yes, you should have gotten, when you did your 9 and your 12, your final length should have been about 15. So we would have had length 9, length 12, and length 15. So that would have been 81 plus a 144, the two areas formed by those lengths, and now a 15 times a 15 is going to be 225. Yes, those match up perfectly. E. The two shortest sides of a right triangle are called the legs. So we got 2 legs on a right triangle. And the longest side, so whichever one is always the longest, that's the special one, that's the hypotenuse. You previously wrote a statement about the relationship between the areas of squares drawn on the sides of a right triangle. Now use words to describe the relationship between the lengths of the legs and the length of the hypotenuse. Okay, so essentially what we're going to get out of this is if I take those, the relationship was always leg A, so whatever the length of leg A was, so we would multiply it by itself. So let's go ahead and just call that leg A squared. Same goes for B. So we could have B squared. And the hypotenuse, the area of that final one. Okay, so I would say out in words that the relationship is leg A multiplied by itself plus leg B multiplied by itself will be equal to the hypotenuse multiplied by itself. And maybe you chose different words, but something along those lines is what you needed to get. Okay, 970. Now we see that kind of written out down here in more algebraic form. The relationship you described in part E of problem 969, that's what we call the Pythagorean theorem. When we're saying that the area of this square plus the area of this square will equal the area of our largest square. It states that a right triangle, the length of one leg squared plus the length of the other leg squared is equal to the length of the hypotenuse squared. There's another great example of how to write it out with words. It can be written in an equation like what we see below. Leg A squared plus leg B squared equals hypotenuse squared. In each of these, you need to identify what is that missing value. Alright, so for A, what I notice is I've got my area, so I've got 9 plus my 34 should equal my final hypotenuse area. So 9 plus 34 is going to be 33. So there's my answer, 33 centimeters squared. There are my two legs. 8 plus a 12 should equal my hypotenuse right over there, so that should be 20. My missing value was 20. Slightly different here. We got one leg is 10, plus we don't know the other leg. Notice our longest side is the 25. So 10 plus something is going to equal 25. Not too hard to figure out. That must be a 15. 10 plus 15 will give us the 25. In lesson 9.2.1, you found a relationship between the squares of the sides of the triangle and the type of a triangle, acute, obtuse, right. You discovered that if the sum of the squares of the two shortest sides in the triangle equal the square of the longest side, then the triangle was a right triangle. Use this idea to determine whether the lengths listed below form a right triangle. So we need to identify if these form a right triangle, and please notice that we are talking about lengths. These are not the areas, these are the lengths of these. Okay, so for A, first I know I've got 15, so 15 squared would be a 225. And then a 36 squared may need to do some quick calculations here. So 36 times 36 would be 1,296, and then 39 feet squared. You're going to add up the area of the first two to see if it equals the final area, and that's what you're going to do in each of these, and then submit your answers. Okay. Finally, you'll find the area of the square in each of these pictures below. Now, they started out with just the length, but once again, we need to know the areas, because it's the areas added together that are going to give us what we're looking for. Okay, so using my areas, I can now add those up to figure out the missing side. Okay, Make sure you're using areas. Submit all of these answers. Make sure you put all the answers on your paper, and have a great day.